No. Um, we're going to take complex numbers to a new level. We're going to start incorporating trig with it. You'll see how that will look. But first off, back in Algebra 2 trig honors, you guys are introduced to this whole concept of an imaginary number, the square root of a negative, more specifically square root of -1. And then also you were told that imaginary numbers are, complex numbers is a real plus an imaginary number. So a plus bi, that's the standard form of complex numbers. A is the real component, b is the imaginary component. The way this is going to work in the realm of vectors and trigonometry, A is going to be kind of like the x coordinate, and B is going to be kind of like the y coordinate. Just so you know, A is going to be horizontal, B is going to be vertical. We're going to think of it in terms of vectors, these complex numbers. A comes before B in the alphabet, X comes before Y in the alphabet. A is horizontal, B is going to be vertical. That's how we're going to think about this. Of course, things that you guys already know. Hopefully, you guys remember multiplying, dividing complex numbers. We could look at that again. We're going to talk about finding powers. We're going to raise a complex number to a certain power. You can see it can be a bit of a pain in the ass. Like if I say, oh, let's do 5 minus 3i raised to the 8th power. Like, oh, crap. Like, how do I do that? There's going to be an efficient way for doing that. That's really neat. Or find the roots. I say, find me the 6th root of like 2 plus 3i. That's going to be kind of weird too. I'll show how we'll do that. By the way, we're also going to find the roots of like whole numbers. And believe it or not, some of these roots will be complex. Like the 6th root of 1, it's not just 1. There's a bunch of complex numbers. It's going to be mind-blowing. So we're going to talk about that too. Before we do that, let's talk about how we can relate complex numbers to x and y, as I just said. So you've been custom graphing real ordered pairs, x and y, you know that. So what if we want to graph a complex number? I know it's kind of weird. How do you graph a complex number? What you do is you call this the real axis, and you call this the imaginary axis. So real goes with A, imaginary goes with B. So if you're asked to do -1 plus 3i, that's just like saying -1 comma 3. So you plot it, and that's it. That's how you plot -1 plus 3i. Oh, it's kind of weird. That's -1 plus 3i. So if you do -2i, where do you think that's going to go? So it's going to be on the y-axis, right? Or the imaginary axis. How about 4 minus 5i? What quadrant? So it's right there. How about -3? In between Q2 and Q3? That's all. Yeah. Pretty simple. So that's how you graph a complex number. So it's not that complex. No one got it? Fine, whatever. Let's try and make a joke. Okay, we'll keep moving. All right. Thanks. All right. All right. Before I do more jokes, absolute value. Okay, so that's hopefully not too bad, right? Okay. Absolute value. Now, before I talk about a complex number, just at its core, like what when you say like absolute -5 or absolute 5 or whatever, what do you guys think of? If someone asks you to define an absolute value, what's the definition, Marie?
It's like the distance.
Yes. From
one number to another, or 0 to a number.
It's the difference between that number and 0 on a number line. So, all right, you don't have to write this down, but from back in the day, maybe middle school, I don't know when you guys learned this, but so when you get outside -4, how far is -4? Like, what's the physical distance of -4 from 0 on a number line? 4, of course, right? Or if I do outside 4, same thing, right? So it's a positive difference between that number and 0. That's what we learned about absolute value. It's the same thing for a complex number, but you're taking the distance from that point to what do you think? The origin, exactly. Correct. So the absolute value of a complex number is purely the distance, as you see underlined here, from the origin. That's all it is. So if I want to find this, right, you don't have to use this as formula. It can make your life much easier. What can you do instead? Yep. If you do Pythag, what do you get? That's it. So the absolute value of -1 plus 3i is just root 10. That's it. Just root 10. If you want a formula, I'll show you down below. But if you think about it, isn't A that number? We should have been -1, by the way. Sorry about that. Isn't B that number? So if I do Pythagorean theorem, when you solve for the hypotenuse, wouldn't it be root A squared plus B squared? Where A is the real number and B is the imaginary coefficient. So that will be true for all these other ones here. Like for -2i, that's 2. For -3, of course, it's 3. For part C, 4 minus 5i, that'll be root 41, I think. Yeah. So for here, if you want a formula, by the way, just to add more letters to your life, Z is another way you can encapsulate a complex number. So the complex number Z, which is just A plus BI. So you want to find the absolute value C of Z, or you could write like this, absolute of A plus BI. What are you going to do? You're just going to do the root A squared plus B squared. So for part A and part B, I just did this, right? That's a 3, by the way. Sorry about that. Let's get root 10. And what was part B? My memory sucks. -2i. So it's just going to be square root of 0 squared plus -2 squared, which just comes out to 2. And I'll be disclaimer here, be honest with you guys, this has no place in AP Calculus BC. You'll never do this in AP Calculus BC. We just have to do this part of the curriculum. We have to do it. You won't see us on SATs. You could see on ACT. So this stuff does, I've seen this on ACT before. Can show up, but yeah. Okay, but it should deepen your understanding of trig, which is good. Because we're gonna start playing some, there we go. Can start talking about some trig here. All right. The trigonometric form of a complex number. This is where we're gonna really spend a lot of time. Let's be present to this like crazy. If you think about it, A is horizontal, B is vertical. So cosine theta, of course, is A over R. Sine theta, of course, is B over R. So A is going to be R cos theta. We kind of understand that now, right? And B is going to be R sine theta. So the way we can think about this, A plus BI would be, and I want to be a little mindful about this because we're using the length of R times cos theta. So I want to be a little mindful about this. For now, I'll just write like with R, but then I'm going to use Z in the box below. So A plus BI can be thought of as R cos theta plus R sine theta times the imaginary number. You can think of it like that. Remember, the imaginary axis is vertical. So B is vertical. So that's why the I goes with B. But really what we're going to do is we use the letter Z instead. So the trigonometric form is given like this. Or sometimes we write it like this. This is going to be a more proper way of writing it. And a condensed way of writing it too. Okay, I'll give you guys a moment to write this down and I'm going to talk about a little bit. So you got to take the absolute value. Sorry, not absolute value. Yeah, it is absolute value. The magnitude. Let's see. Which is that? Which is the absolute value, right? We know that. So the magnitude of z times cos theta plus absolute value z, or the magnitude of z times sine theta I. You can factor out the magnitude of z. Factor it out. So you have cos theta plus I sine theta. You either like to write I before sine, because it can be a little hard to see if you put it to the right. So you like to write to the left. So that's kind of the standard. Now, another way you can write this too, because mathematicians are really lazy, you can abbreviate it. Absolute z cis theta, CIS, cis theta. The CIS essentially combines cosine, sine, and I. That's where it comes from. CIS, cis theta. So so if you see that, or if you work with a tutor, or you just go online and look at stuff, you might see that. You might be a little confused. That's all it is. Just cosine, I, sine combined. So A is going to be the absolute z, or magnitude of z, cos theta. And the B is going to be this. And the R is just this. Well, we actually know R is this. Well, tan theta is B over A. Yeah. Yeah. Yep. 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 Same thing. That too. Yes. Same thing. Yep. So we call it the modulus of Z, meaning, well, the magnitude of Z is R. And it's called the modulus, some fancy name. I don't care. It's called the argument of Z. I don't care. So in a way, it's a polar form. And there's going to be several ways we can express this because there's several choices for theta. We'll talk about that later. Okay, so before I go any further, just so we're clear, A is a real number, B is the imaginary coefficient, Z is the way we can combine A and B, so Z equals A plus BI. A is going to be the magnitude of the complex number times cosine theta. B is the magnitude of the complex number times sine theta. And remember, to find the magnitude, just do root A squared plus B squared. To find the angle, we got to do tan theta equals B over A. So just using a lot of the basic trig knowledge we have. These problems won't be too bad. It does get a little crazy later on, so brace yourself for that. But crazy is okay. So this one here, you're asked to write each complex number in trigonometric form. Assume theta is between 0 and 2 pi, and possibly express all values exactly. Sometimes we may have to round, so we'll see. I think we have to do it for part B. So what I'm going to do is I need to find the absolute value z, or the magnitude. And I also got to find theta. So how do I find z? What am I going to do again? How do I find the magnitude? Yeah, pi theta, that's all. Which by the way will be 2. That'll be 2. And it's always a positive value, by the way. Always, always, always a positive value. Like your speed, when you're going, like, you're not going to say, I was going south, no, I'm going negative 50 miles an hour. No, you're still going 50 miles an hour. It's magnitude. It's positive. Cops don't believe that. Don't try that. If anyone does try that and gets off from a ticket and you can show me proof, won't give you an A in the class, but I'll do something very nice for you. I'd love to see that. I highly doubt because you guys are too young. They want to know you guys, especially boys. If you get pulled over by a cop, like for speeding, you try to use the excuse, oh yeah, but like I thought I was going negative 50 miles an hour because that's my velocity, not my speed. Because I went south. Right. Wow. See. Okay. Anyhow, or you just deliberately just go fast, but don't do that. It's dangerous in the wet weather. So, okay, this one right here. If you think about it, what quadrant am I in here? 4. So we need to find that angle. And we did say we're going from 0 to 2 pi. But this is a unit circle situation. That's going to be what? Reference angle is 60 degrees, I think. Is that right? Yeah. So that's going to be what? 5 pi over 3? By the way, we're going to have to use radians for most of the stuff, just so you know. So kind of get used to that. We have to use radians.
So for stuff is 4, 5 degrees.
Well, for bearings like vectors, yes. But this stuff, yeah, we're going to be using radians.
The bearings, do you rotate clockwise or counterclockwise?
Clockwise.
Clockwise?
Clockwise, yeah. From the north. You go clockwise.
But on the homework, sometimes it goes kind of.
Depends on what was being asked because there's different scenarios. I have to look at the question. Yeah. If it's direction angle is counterclockwise, or if it's like south of west, which I'm not sure if that was in there. I'll up.
Something like that.
Yeah, we'll look. So okay, so once I have that figured out, then here's what you do, guys. You're gonna write your answer like this: Das value of z cos, or actually, I don't know why I put parentheses. That was dumb. As value of z cos theta plus as value of z, or I, as value of z sine theta. So I can write like this: 2 cos 5 pi over 3 plus 2i sine 5 pi over 3. I can factor out the 2. Right, like this. Or I can also write like this too. So that's just yet another way of writing a complex number in trig form. And plus, if you work it out, cosine 5 pi over 3, I know is 1/2. I know sine 5 pi over 3 is negative root 3 over 2. So I know it makes sense. If I evaluate it, it makes sense. It's yet another way of writing it. Why do we have this? You'll see when we get to the more challenging, I'll say complex, I want to make any more jokes. More challenging questions when we have to like start multiplying these by themselves, or we have to raise these to other powers. There is some more advanced math that, like, if you for the sophomores, it might do ATMH, the advanced topics class. I do think they revisit this. If you major in math or take some crazy math classes, these are skills that you kind of need to know to handle those classes. But for calculus, it has no place. So it's kind of weird that's in pre-calculus, but we have to cover it. And actually, I'll show you where you can do this in the calculator too. Do you guys know where to find imagine numbers in the calculator? It is there. Right below, you see the decimal point? You see there's a little I there? That's imagine a number. So you could do 2 parentheses cosine 5 pi over 3 plus second decimal point. So you have that now. So 2 parentheses cosine 5 pi over 3 plus I sine parentheses 5 pi over 3. And I think I'm in radian mode. I am. And you do have to switch this to A plus BI. You do have to go to mode and go down to the middle, so it actually will give imaginary numbers. and it will give me that. And I know that root 3 is 1.73. So you could always use it to verify your work. And there's other ways that's going to be very helpful too, with the later examples we'll do in this set of notes. But yeah, that's one way you could write it. If you go to Desmos might be able to do sys. Let's see here. If I do 2 sys, 5 pi over 3. No, it doesn't like sys. It doesn't know what to do with that. Should talk to Desmos about that. Cosine 5 pi over 3 plus I sine. That's dumb. Why does it ask for a slider? Really?
Settings you can change.
Ah, good. Yeah, Kingston. That's why we're gonna use your test to. Yeah. Look at Kingston. Kingston, you're awesome. Thank you. Yes. Settings. You know what? Maybe sys will work now. 2 sys. No, I don't think it likes sys. Never mind. Anyway, you got that right there. And it plots for you too. Yeah, there we go. Okay.
What'd you say?
Complex at the bottom. Yeah, there we go. Okay. So let's look at part B now. For part B, I think we'll go a little faster here. After I have Z, we kind of know what do you think that's going to be? If you have 3 and 4 is 5, yeah. It's just let's not beat the bush, beat around the bush here. We know that. And then here you're doing of -4 over -3. Now this I have to use a calculator. I use my handheld just to save time. Remember to stand 4/3. Got to switch to radio mode. 0.927. However, this has to be Q3. Correct. It has to be Q3. So I have to add pi to this. Plus pi will be 4.069. So when I write the answer, it's going to be 5 times cis of 4.069. That's how I can express that complex number in trig form. So once you get the hang of it, you don't have to be so long-winded about it. You say, yeah, it's fine. I know the magnitudes, I know the angle, adjust it for the right quadrant, and boom, you got it. And it'll get you that same thing. And if you were to actually go back to Desmos again.
You want us to write it like this,
Yeah, sure.
but if we really like what about it.
But if you verify in a calculator, I just doesn't seem to like, it doesn't know what sys is, so I have to do this instead. But you can see, like when I do in Desmos, it's pretty darn close to -3 minus 4i. I mean, it's obviously I approximated the angle, but it's pretty darn close. But you can write sys, yeah, that's fine. Yeah, just an abbreviation. Why not?
We can do either way.
It's up to you. All right, so we're okay with that. Now for here, you're asked to write the complex number back to standard form. So going back to the other direction, that's pretty easy. Just evaluate it, right? Ask me what's cosine 2 pi over 3? Yep, 1/2. And that's oh, you're right, -1/2. My apologies. And root 3 over 2. And root 8, by the way, can we rewrite that? Yeah, that's smart. So that's me -2 and plus I root 6. Wait, hold on, I make a mistake? What did I do wrong? Oh, sorry. Yes. The first one. Okay, cool. Right. Negative root 2 plus I root 6. You guys agree with that? Yeah, cool. Okay. Yeah, and again, you could always verify this in Desmos. So if I did square root of 8 parentheses cosine parentheses 2 pi over 3 plus I sine 2 pi over 3, I get that. And if I do negative root 2 plus square root 6 I, you get the same thing. So you can also verify your work here. And most likely I'll probably allow Desmos again. So okay, so we're cool with examples 3 and 4. All right. So let's move on to the next page. Okay, this is where the fun begins. Okay, so dividing and multiplying, dividing complex numbers. You guys probably knew what to do in Mr. Band's class. I'm going to show you a better way because you guys now know how to do some trig form. And it's actually going to be better doing some trig form. Then we'll do powers and roots after that and see how far we can get. Do you mind maybe taking a... Actually, I can take a screenshot of this in the email to you. You sure you got it? Okay. All right. Okay, let's move on to the next page. All right, multiplying, dividing. So there's a proof that goes with this. Actually, we should do, it is a cool proof. Let's do the proof. If you're multiplying, you're doing Z1 times Z2. So you're doing this. R1 cos theta 1 plus I sine theta 1 times R2 cosine theta 2 plus I sine theta 2. Looks like an extra parentheses there. That didn't make any sense. Let's get rid of that. Okay. Well, I'll multiply R1 and R2 together. That makes sense. Excuse me. Then I'm going to do some foiling. Excuse me. So I'll do cosine theta 1 times cosine theta 2 plus I sine theta 1 with cosine theta 2 plus I sine theta 2 with cosine theta 1 plus I squared. And I'll take a little break so you guys can copy stuff down. Sine theta 1 times sine theta 2. Okay, I'll take a little break so you guys can jot that down. So you guys saw I foiled, right? Cosine theta 1 with cosine theta 2. I sine theta 1 with I sine theta 2, which is I squared. What's I squared, by the way? Negative 1. Negative 1. I sine theta 1 cosine theta 2. I sine theta 2 cosine theta 1. Cool. Good. Okay. All right. Here's what's gonna happen. Does anyone have an idea what I'm gonna do next? Yeah. I'm gonna be using a trig identity. Things will cancel somewhat, kind of. No thoughts yet? All right, we'll see. Yes. There you go. I could just give you the form, but I wanted you guys to see this in all its glory. Okay, I know it looks a little blacker right now. I just did a rearrangement. Cosine theta 1, cosine theta 2, we know that, right? I squared is -1, but I brought that I squared sine theta 1, sine theta 2 closer to the left, next to cosine theta 1, theta 2, was negative sine theta 1, sine theta 2. And then there's two things that I know, sine theta 1, cosine theta 2, sine theta 2, cosine theta 1. In fact, I've done. Take a look at this. What's going on here? What identity is that? Someone just said it. The difference formula. Difference formula. For what? Good. Yes. So that's going to equal R1, R2 cosine of theta 1 plus theta 2. I'll get a little highlighter here to emphasize that.
Is the next one sine?
Yes. You guys remember that, right? Sum formula, which I'll give to you guys, don't worry. Plus I sine. And here you got sine theta 1 cosine theta 2, sine theta 2 cosine theta 1. There's a plus in the middle. That's a plus also. Remember, the cosine's always the opposite because it has that minus plus part in the formula. So that's the proof. When you multiply two complex numbers, now granted, multiplying complex numbers is pretty easy in the a plus bi form. It's not that hard. But this technique is going to help tremendously with some of the more advanced stuff we do in his notes. So if you take your complex number, convert it to trig form, so you have this in trig form, this in trig form. If you're going to multiply those two complex numbers, if you have the angles for each complex number, add the angles. Plug it into that formula. And then if you have your two magnitudes, multiply them together on the outside. And that's how you can multiply complex numbers. Dividing will work the same way. Dividing complex numbers is actually more challenging because you might remember if you had like 2 minus 3i or 4 plus 3i, you had to find the conjugate. Remember doing that part? Maybe, kind of. I'll remind you guys. I'll show you how that works. And that was a bit of a pain. It's going to be easier using a similar process for dividing complex numbers. So to sum up the proof, I'm not going to prove that the quotient is going to take too long, but just to kind of summarize this, you're going to do R1, R2, cosine, my apologies, cosine theta 1 plus theta 2 plus I sine theta 1 plus theta 2. Now, for division, what do you think is going to happen instead? R1 over R2. And it's going to be analogous. What's the inverse of addition? Just like how division is the inverse of multiplication. Don't worry, I give you guys these formulas. I'll give them to you, don't worry. In fact, I actually give a lot of the complex formulas, so don't worry. That's how you divide complex numbers. So here you're asked to find the product expressed in a plus bi form. Great, let's do it. So z1, z2 is going to be 2 times 8 times bracket cosine. I'm going to make that 4 pi over 6, so it's easy to add to 11 pi over 6. And you can always verify this in the calculator or in Desmos. I'm not gonna do that in the interest of time, but now you know how to verify your work. So you could totally do this in Desmos to, or sorry, TA4, either one to verify. $15 pi over 6? Is that right? What does that reduce to? Is that 5 pi over 2? I reduced it. Right? They're both divided by 3? I think so. I don't know, I could be wrong. I don't know. Subtracted. Oh, you made it 3, 5, or 6.
Yeah.
Same thing. Yeah. Cosine 5 pi over 2 I know is 0. That is 1. 69. That's just 69. It's that simple. That's just 69. Okay, let's keep going. Questions? All right. I think you guys can handle example 6. We'll check in a couple minutes. Try example 6. Now, I did lie. There is some degrees here. Fine. We'll deal with it. It's okay. You're dividing. It froze my screen. You guys try it. We'll check in a couple minutes. So back in the day, when you guys divide complex numbers, when I'm writing in red, you don't have to copy. But when you have like something like 4 plus 3i, or like 1 minus 2i, do you guys remember how to do that problem? What would you multiply top and bottom by? Yeah, and it got to be a little bit challenging because you had to like be very careful with all the maneuvering you're doing and this and that. You had to simplify afterwards. That's the one beauty about converting to trig form, is if you have it in trig form, you just combine the angles and combine the r's and you're good, right? So well, I think what I'd probably do is I'd probably give you maybe, I mean, I have to look at the old test, but I think I would say, here's a complex number, convert it to trig form, and then afterwards, hey, let's multiply these. But actually, I'm going to show you something more challenging. Let's raise it to like the 5th power, because if we FOIL that to 5 times, you're going to go crazy. There's a faster way, which I'll show you in a moment, using a similar process. Does that make sense? We get that one? Okay. Now powers and roots. I think we'll do powers. We'll save roots for next week, because I might get a little, because I don't want to rush it. So I think we'll do examples 7 and 8, and then we'll Demois. It's French. Yeah, I don't speak French, but anyway, it's Demois. All right, here we go. Okay, so last part for today. We'll talk about powers. We'll save roots for next week. So let's say you got, yeah, 3 plus 4i raised to the 5th power. You do 3 plus 4i multiplied 5 times without a calculator. That is crazy, right? That would be nuts. You don't want to do that, right? So now I could do a problem like this as a non-calc problem, but I give you something where the angles are easy to find using unit circle. Obviously, this is gonna be a little tricky using unit circle. But to multiply it 5 times is nuts. So if you think about what's happening here, z squared is not just z times z, right? So if you think about it, you could just say r squared times bracket cosine 2 theta plus I sine 2 theta. Right, because aren't you just doing this? Aren't you just multiplying by itself, right? And what did we see earlier? You would just add these two angles and add these two angles. What's theta plus theta? Yeah, same thing here. So you could think of it like that. So as we go through the pattern, what's going to happen? R cubed, R4, R5, cosine 3 theta plus I sine 3 theta. Cosine 4 theta plus I sine 4 theta. And by the way, we're not going to go over homework today. We'll save it for next week. It's fine. Plus I sine 5 theta. So what do you notice about z to the n? It's just going to be r to the n times cosine n theta plus I sine n theta. That's called Dumois theorem. It's simply r to the n. I'm going to write it again, sorry. Times cosine n theta plus I sine n theta. That's a way you can streamline this process. That's what I was saying, like, yes, multiplying complex numbers, if you did an a plus bi form, just leave it like that. Don't switch trig forms crazy. But we had to see that to understand this process, right? Because now I understand it. Now if I'm multiplying z with z, I'm just adding theta to theta, right? And I see this as a pattern that's happening now. I can show you, I can prove z3, z4, z5, but you guys will see the pattern, so why I don't need to do that. You guys see that pattern. So if I ask to raise 1 plus I root 3 raised to the 3rd power using Dumois theorem, I don't need to FOIL 1 plus I root 3 times. That's crazy. Don't do that. Just use this formula. That's it. But before I do that, let me make sure everyone's got this here. Everyone's okay? We're okay. We're good. Okay. So here, let's try it now. Let me put some stuff here. Let me move this. Here we go. Okay. So what you need to do first is figure out what R is. Figure out what theta is. What's R here? Or the absolute Z, same thing. 2? What's theta? A squared plus B squared. Same thing as absolute Z. Pi over 3. Pi over 3. Yep, theta is pi over 3.
Wait, is tangent of data just the overhand?
Correct, right. And you're in Q1, guys. A and B are both positive. You're in Q1. Okay, let's do it. 2 cubed times cosine of 3 times pi over 3 plus I sine 3 This I could totally ask a non-calc question. I think this is fair. Because this is testing your knowledge of unit circle. You do not need a calculator for this. Done. Negative 8. A squared plus b squared. A is 1, a b and 3. Planning and firm, you're going 1 this way, and you can that way. 1 plus 3 is 4. Your hypotenuse is 4. So just back. Do you graph it? Yeah. Remember, 1's right here, root 2's right here. That's 1, that's root 3. Let's see. It's just patterns that's all I'm doing. By the way, the cube root of negative 8. You guys know it's negative 2. You've been taught that your whole life. We've lied to you. That's not just negative 2. What's the cube root of negative 8? Negative 2 as well as 1 plus I root 3. And 1 minus I root 3. The cube root of negative 8 is not just this. It's also this. Because if I go backwards, I should get that, right? Of course I should. Yeah, I know, it's mind blowing, right? We'll save that for Monday, because I don't want to do that today. But let's try one more of these. Before I do this though, if I were to FOIL that, that is crazy, right? To do 1 plus I root 3 times 1 plus I root 3 times 1 plus I root 3 and do all that foiling and combining of i's, you're gonna go crazy. Don't do that. See how much easier that was? That wasn't that bad, right? If you FOIL that, that's gonna take some time. I'm not gonna do it in the interest of time. Maybe next week I could show you like why you would not want to do that. But you know, if I go to Desmos and do what was it again? 1 minus 1 plus I root 3. Yeah, there we go. Yeah, duh. So 1 plus I square root 3 raised to the third power. Okay, it's kind of funky. Don't let the scientific notation fool you. Negative 8 plus 8.818 times 10. What does that mean? 10 to the negative 16. Super small, right? Why is it doing that? It has a funny algorithm where it's approximating. I don't quite fully understand the algorithm. I should maybe come more review a little bit, answer that question to Solomon. But there's a funny algorithm that's happening here. But essentially that's just 0 I. But you could do that. Totally. Okay, I think you guys could handle, try example 8, and we'll stop there after today. Try example 8. What quadrant are you in, guys? Q what? 2. Good. Good. Well, no, so you know you're in the second quadrant. You can only have one value. Yeah, but yeah, it could be another quadrant. But remember, our A is negative, our B is positive. We're not going to be Q4. Yeah, I mean you can go around many times you want, but you're still going to end the same value. Won't matter. Remember, we raised it to the 5th power. It's gonna be. I think I got it.
Yeah.
Yeah. You see how so much easier that is? It's way easier to do it this way. As opposed to boiling. So this is the advantage of doing this in trick form. So I'm glad at least we got to see that. Yeah, I think it's best to kind of stop here because the routing is a little funky. It involves actually a lot of K's. I told you the K stuff's going to come back with a vengeance. It does here. when we do the roots, that's gonna involve the letter K. Yeah. Hopefully the lesson's not too complex. You guys get that? No? No, all right. Anyhow, homework is gonna be, hold on a sec. You're not gonna do all the homework, because I haven't done the roots yet with you guys. So let me tell you what I want you guys to do for homework. Don't do 11 through 13. You're just gonna do 1 through 10. Just 1 to 10. Okay. It's 1 to 10. Don't do 11 to 13. 1 to 10. I'll finish closing from here. You have the answer, check your work.
Oh, okay, yeah. I like to hold my own with people like that. I mean, that's some. The time groups, let's say, I mean, it's like, the reason why. I didn't go.